Computer Science 407, Numerical Analysis, Section 1.2, Mathematical Preliminaries. This section covers some of the things you probably forgot about Calc 1 and Calc 2. Specifically, there's a focus on Taylor series, the mean value theorem, alternating series, and computer number representation. If you don't have a great handle on these things, you may want to go back and take a look at your calc text to make sure that you understand them. The authors say that if you're well prepared that you can skip over some of this material. But this section is important for scientific computing. Taylor series come up again and again and again throughout numerical analysis. So it does require some careful study, and I recommend that you take your time. We're going to have a lab on this so that you'll be familiar with how to actually do this stuff in practice. So, keeping that in mind, this material comes from Warburg, Purcell, and Brigden's Calculus with Early Transcendentals, the instructor's edition. And again, it's worth a review of calc if you're not familiar with this stuff. I actually grabbed my calc book and reviewed and brought up these slides. So, if we have a function f, for example, the sine or the natural log of the cosine squared of x, can we represent it as a power series in x, or more generally in a series of x minus a? So basically we can find numbers c0, c1 such that f of x is approximately equal to c0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed, etc., etc. And basically, the uniqueness theorem says that if f satisfies f of x is equal to c sub 0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed, etc., for all a in some interval around a, then c sub n is equal to the nth derivative of f evaluated at a divided by n factorial. So, according to the uniqueness theorem, a function cannot be represented by more than one power series in x minus a. The power series representation of a function in x minus a is called its Taylor series, after Taylor of all people. If a is equal to 0, then we have a Maclaurin series, and of course those were named after Maclaurin. So let's take a look at Taylor's formula with a remainder. So we'll have f be a function whose So we'll have f be a function whose n plus first derivative, f of n plus 1 prime of x, exists for each x in an open interval I containing a. Then for each x in I, f of x is equal to f of a plus f prime of a times x minus a plus f double prime of a divided by 2 factorial x minus a squared, all the way out to the nth derivative of f, evaluated at a, divided by n factorial, times x minus a raised to the n, plus some remainder r sub n x, which is given by the formula of the n plus first derivative of f, evaluated at c, n plus 1 divided by n plus 1 factorial, times x minus a raised to the n plus 1, where c is some point between x and a. And basically this theorem tells us what error we can expect when we approximate a function with a finite number of terms in its Taylor series. It also gives us the power series for the function. Now, we're interested in finding out whether a function f can be represented by a power series in x minus a. And this is Taylor's theorem. So, let f be a function with derivatives of all orders in some interval a minus r to a plus r. The Taylor series, f of a plus f prime of a, x minus a, plus f double prime of a, divided by 2 factorial, x minus a squared, etc., represents the function f on the interval a minus r to a plus r. And here's the if and only if so goes bidirectional. The limit as n goes to infinity of the remainder is equal to 0, where the remainder is the remainder from Taylor's formula that we looked at in the last slide, which is the n plus first derivative of f evaluated at c divided by n plus 1 factorial times x minus a raised to the n plus 1 power, and c is some point between a minus r to a plus r. And again, if we set A equal to 0, we have the Maclaurin series. The authors use C instead of A, but the idea is still the same. So let's take a look at an example and we can clarify some things. So we can find the Maclaurin series for sine of x and show that it represents sine of x for all x. So the first thing we need to do is start taking some derivatives. So we know that f of x is sine of x, and if we evaluate sine at 0, we get 0. Now the derivative of sine is cosine of x, and that's again something you'll have to refresh from calculus, and cosine of 0 is 1. Now the derivative of cosine, which is going to be our second derivative, is minus sine of x. So the second derivative minus sine of x evaluated at 0 is minus 0, which is 0. And the third derivative is going to be negative cosine of x. And cosine of 0 is 1, so f triple prime, or the third derivative of f, evaluated at 0 is minus 1. And things begin repeating because the derivative of minus cosine of x is going to be positive sine of x. So we repeat these every 4. So sine of x can be evaluated as x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial minus x to the 7th divided by 7 factorial, and the limit of any remainder term is going to go to 0 since the n plus 1 factorial term in the denominator dominates the discussion here. So here are some quote, familiar and useful Taylor series, end quote, from Cheney and Kincaid slides. I sort of remember these from 25 years ago in the same way that I remember Axl Rose being skinny. It's been quite a long time, and these ones come up again and again and again, so it's useful to keep these in mind. If you're keeping a crib sheet for a test, I would include all 5 of these equations on it. Anyway, for each case, the series represents a given function and converges in the interval that is specified for x. So let's take an example of how to use some of these familiar and useful Taylor series. We can use 5 terms in the natural log of 1 plus x series to approximate natural log of 1 plus 1. Taking x is equal to 0.1, we have the following 5 terms. Natural log of 1.1 is approximately equal to 0.1 minus 0.01 divided by 2 plus 0.0001 divided by 3 minus 0.0001 divided by 4 plus 0.00001 divided by 5, and it comes out to about 0.09531, 0 repeating 3's, and the result that I got on the calculator with my computer gave 0.9531079. So this is actually pretty close. The authors also cover how to compute e raised to the 8th using equation 1. In that case, there were far more terms needed to get a good result, and that leads us to a general rule. Basically, Taylor series converge rapidly near their point of expansion, and slowly or not at all at more remote points. So consider the Maclaurin series for sine of x around c is equal to 0. S1, the first term, is going to be x. S2 is x minus x cubed divided by 6, and S3 is x minus x cubed divided by 6 plus x to the 5th divided by 120, which is the 6 factorial, or 5 factorial. And so, yes, this is labeled as a rule of thumb, and the graph shows the results that we get when we plot those. So you can see sine of x as the dotted line. S1 is the linear line that represents x. S2, you can see that we're actually getting a bit closer to it, although it diverges very far at the endpoints. and S3 begins coming very, very close to the actual sign of x functions, or S5 ends up being very close. So this graph is from page 23 of the text and shows that we can get a pretty good approximation of f of x at x equals a by taking only a few terms of the Maclaurin series. In this case, we can see the purple line with 3 terms is starting to get very close to f of x is equal to e of x. Hopefully this will be sufficient background on Taylor series, since we're going to be using them throughout the book. If you're still somewhat lost, make sure to check your handy calc book or see one of the handy math professors, because they know this quite well. We're now going to take a look back at Horner's algorithm and see how it can be used to find Taylor series expansions of a polynomial about a point. You'll remember Taylor series from the first lecture in this class. So this is the complete Horner's algorithm, and basically Horner's algorithm can be applied to find a Taylor series expansion about a point. If we let p of x be a given polynomial of degree n with coefficients a sub k, and we want to find the c sub k in the Taylor series expansion, basically Taylor's theorem is going to tell us that c sub k is the kth derivative of p evaluated at r divided by k factorial. But we'd probably like a bit more efficient way of doing that because we don't necessarily want to do all those derivatives. So here's the so at p of r is equal to c of 0, this coefficient is obtained by applying Horner's algorithm to the polynomial p at point r. And then the algorithm also yields q of x, where q of x is p of x minus p of r divided by x minus r, and that approximates c sub n x minus r to the n plus 1 plus cn minus 1, etc., all the way out to c1. So we can get c1 by applying Horner's algorithm to q of x at point r, and we repeat this process until all coefficients c sub k are found. We're going to call this the complete Horner's algorithm, and we'll take a look at some of the pseudocode here. Here's the pseudocode for the complete Horner's algorithm. The pseudocode for executing is arranged so the coefficients c sub k overwrite the coefficients a sub k for efficiency, but that's about the only efficiency they put in it. And basically, this algorithm can also be used in carrying out Newton's method for finding roots of a polynomial, and we'll see that in chapter 3 of the text. So let's illustrate this with an example, and you'll recall synthetic division from the first lecture and probably from the first lab, so you should be familiar with it. And so we'll just use Horner's algorithm again and again until we get the results we want. So here we're going to use the complete Horner's algorithm to find the Taylor expansion of the polynomial p of x is equal to x to the 4th minus 4x cubed plus 7x squared minus 5x plus 2 about the point r is equal to 3. So what we do is we use our synthetic division to have 3 go into that polynomial. So we put a 0 in the first, and 1 plus 0 is 1. Multiply 3 by 1, we get 3. Minus 4 plus 3 is minus 1. 3 times minus 1 is minus 3. Put that over underneath the 7. 7 plus minus 3 is 4. 4 times 3 is 12. Minus 5 plus 12 is 7. 3 times 7, 21. 2 plus 21 is 23. Now we take that result, the 1 minus 1, 4, 7, and we perform synthetic division again on that. From there we get 1, 2, 10, and we bold the 37. Then we put 3 into 1, 2, 10, we get 1, 5, and 25. And we have 3 go into the 1, 5, we get 1 and 8, we bold those terms. And then at the end we take the bolded numbers from bottom to top and form the polynomial. X minus 3 to the 4th plus 8 times x minus 3 cubed plus 25, next bolded number, x minus 3 squared plus 37 x minus 3 plus 23 from the first synthetic division we did. So let's take a look at the pesky error term. Because in practice we usually have to truncate, because we can't have an infinite number of additions. I don't have time for it, and you probably don't either. So we can actually use this error term, which is the remainder, which is equal to the n plus first derivative of f evaluated at point C divided by n plus 1 factorial times x minus a to the n plus 1 to see how far off we are. The text uses some slightly different notation for the error term. Regardless, this is the Lagrange form that you probably want for the error term. You can also use the error term to determine the range for positive x for which the series represents the function. And if you want to see an example of that, it's on example 6 on page 26 of the current edition of the textbook. This brings us to the mean value theorem, which again is probably something that you've forgotten from calculus. And the special case where n is equal to 0 in Taylor's theorem is known as the mean value theorem. By the way, the squiggly thing you see there is xi, because Greek letters help to make things more confusing. So let's take a look at the mean value theorem. It says if f is a continuous function on the closed interval ab and possesses a derivative at each point of the open interval ab, so that's not including a and not including b, then f of b is equal to f of a plus b minus a times f prime of xi for some xi in ab. So let's simplify for a minute here. This theorem basically says there's some value xi in the interval for which the derivative of f of x is equal to f of b minus a, or f of b minus f of a divided by b minus a. And there's a corollary to this. It says if a function f possesses continuous derivatives of order 0 to n plus 1 in a closed interval I that runs from a to b, then for any x in I, f of x plus h is equal to the sum k equals 1 to n of the kth derivative of f evaluated at x divided by k factorial h raised to the k plus e sub n plus 1, where h is any value such that x plus h is in I, and where e of n sub n plus 1 is equal to f, the n plus first derivative of f evaluated at xi divided by n plus 1 factorial h raised to n plus 1. And so basically we can say that the error term is O of h n plus 1. There are other forms that can be derived from Taylor series for f of x by changing the variables a bit. Here we can change x to x plus h and c to x. In particular, this corollary is known as Taylor's theorem for f of x plus h. The error term here depends on h in two ways. First, h raised to the n plus 1 is explicitly present, and xi generally depends on h. As h converges to 0, e of n plus 1 converges to 0 as rapidly as h raised to the n plus 1 converges to 0. For large n, this is pretty fast, and so the error term may seem like an afterthought, but it's actually pretty important. In later chapters and later material, we'll frequently require an estimate of errors in a numerical process that's defined by the use of Taylor series. Let's take a look at an example of where we can use this form with f of x plus h. So here we want to expand 1 plus h in powers of h, and then compute 1.00001, the square root of that. So basically we need to find some derivatives here, because we always need to find derivatives for Taylor series. So the first one, f of x, is equal to the square root of x, which is x to the 1/2 power. The derivative of that, we bring the half down and then subtract 1 from the power. So it's 1/2 x to the minus 1/2. Again, bring the minus half down. For the second derivative, 1/2 times minus 1/2 is minus 1/4, x to the minus 3/2. And the third derivative, we multiply minus 1/4 times minus 3/2, which gives us 3/8, and we subtract 1 from the exponent to get minus 5/2. We can then use corollary 1 with x is equal to 1. And for n equal to 2, we have 1 plus h is equal to 1 plus 1/2 h minus 1/8 h squared plus 1/16 h cubed times xi to the minus 5/2. And xi is going to be somewhere between 1 and 1 plus h if h is greater than 0. If we let h equal 10 to the minus 5, which is what we have there, the 0.00001, then the square root of 1.00001 is equal to 1 plus 1/2 times 10 to the minus 5th minus 1/8 times 10 to the minus 10th, and we get about 1.0000499998750. And if we wanted to actually derive the square root of 0.99999, then we could use minus h instead of h, and the example works out similarly. Note the error term here is going to be 1/16 times 10 to the minus 15th, and that's going to be pretty darn small. It's going to be 0.151600625, which is pretty darn small. So that's going to give us a pretty good estimate on this. And Taylor series can give us pretty good estimates of functions. Another thing that you may have forgotten from calculus is alternating series. And these are series that have successive terms that alternate between positive and negative. And the principle of alternating series says if the magnitude of the terms in an alternating series converges monotonically to 0, then the error in truncating the series is no larger than the magnitude of the first omitted term. We're going to express these ideas a bit more formally in the alternating series theorem, and we can use these principles to establish the convergence of a series and to estimate the error involved in any truncation for an alternating series. And again, it's the first omitted term is going to be the key to this. So the alternating series theorem tells us if A1 is greater than or equal to A2 is greater than or equal to A sub n, which are all greater than 0 for all n, and the limit as n goes to infinity of A sub n is 0, then the alternating series A1 minus A2 plus A3 minus A4 plus A5 minus A6 converges, and that the sum of this series, minus 1 to the k minus 1 a sub k, is equal to the limit as n goes to infinity of the series k equal 1 to n minus 1 to the k minus 1 a sub k, which is equal to the limit as n goes to infinity of s sub n, which is equal to s, where s is its sum and s sub n is the nth partial sum. And moreover, for all n, s minus s sub n is less than the first omitted term. And this was a lot of nasty typing. So let's take a look at how we can apply this theorem and the principle of alternating series to get a bound on how many terms are needed for an alternating series given a particular error. So if we're interested in the sine series to be used in computing sine of 1 with error less than 1/2 times 10 to the minus 6, how many terms do we need? Well, we look back at our familiar and useful Taylor series, and we know sine of x can be approximated by x minus x cubed divided by 3 factorial plus x to the 5th divided by 5 factorial, etc., etc. And sine of 1 is 1 minus 1 over 3 factorial plus 1 over 5 factorial minus 1 over 7 factorial, etc. If we stop at 1 divided by 2n minus 1 factorial, then the error term is not going to exceed the first neglected term, which is going to be 1 over 2 to the n plus 1. So what we factorial. So what we actually want is 1 over 2 over 2n plus 1 factorial to be less than 1/2 times 10 to the 6th. And basically using some logarithms, to the base 10, log of 2n plus 1 needs to be greater than log of 2 plus 6, greater than 6.3. And a little trial and error reveals that log of 10 factorial is 6.6. So if n is greater than or equal to 5, then the error will be acceptable. There are another couple examples of this on page 30 and 31 that should be worth reviewing prior to the lab. As a word of caution, this technique only works on alternating series when the terms go to 0. However, it can sometimes be used in other circumstances to obtain rough estimates in other cases, particularly if the series converges slowly. In any case, be careful with applying in circumstances where it's not warranted. You can get in a lot of trouble in mathematics doing that. So, in summary, the Taylor series expansion about C for f of x and its error term were covered today, as well as a more complete version of Horner's algorithm that can be used to find the Taylor series expansion about a point. And we talked about the Taylor series expansion for f of x plus h and its associated error term. And finally, we talked about the alternating series principle and an easy calculation of the error term for alternating series. Next time we'll look at floating point representations in the computer and some of the subtle problems we can face with digital representation of these numbers.